This is chapter 8 or chapter 7 sa book of Fowles and Cassidy. So we are now on Lagrangian mechanics. So we know Newtonian mechanics, right? We know how to solve problems, mechanical problems or dynamical systems using Newtonian mechanics. So another method on solving uh, mechanical problems, classical mechanical problems, is we have this Lagrangian mechanics. Okay, so we have Lagrangian mechanics. Okay, so Lagrangian mechanics. So si Lagrangian, tao ni siya, si Lagrange, no? Tao ni si Lagrange. Okay, so we have the Lagrangian mechanics. Okay, so Lagrangian mechanics, it is postulate, used to postulate known, use the postulate, sorry, it uses the postulate, we call this one as Hamilton's variational principle, okay, known as Hamilton sa math. Popular ni siya nga principle sa math. We call this one as Hamilton's variational principle. Okay, so we will tackle this one later. What do you mean by Hamilton's variational principle? So ang Lagrange mechanics is gagamit siya ani nga postulate kaning Hamilton's variational principle to show the that in the specific case, okay, of a body, say falling in a uniform field, falling in a uniform field or gravitational field, it is equivalent to Newton's laws of motion, Newton's second law of motion. So later, we will try to prove na if I'm using Hamilton's variational principle sa usa ka problem like na ako'y object that is uh, moving downward or that is freely moving downward because of gravity, ma-show na to or ma-verify na to na kaning Hamilton's variational principle kay ma-derive na using this ma-derive na ko ning Newton's second law of motion, which is equal to F equal to ma. Okay, so actually ang Lagrangian, the Lagrange equation is somewhat you can relate that to the Newton's second law of motion. Okay, the Newton's laws of motion. Okay, so later ato anang i-prove, no, once I have the Lagrange equation masolve nimo ang Newton's laws of motion or makakuha ko equation from Newton's laws of motion, which is katong nakoy duha, no, F equals 0 and F equals ma. So actually same ra sila, no, na sila related silang duha, no, sila related ning Lagrangian o Newtonian mechanics, so naa siya somewhat connection. Okay, so in this case again it used the postulates, this Hamilton's variational principle postulates to show that if I have a problem, say free falling object, the method that I use is mo padulong siya or mo ma-prove nimo ning equal ni imong equation using Hamilton's variational principle to the Newton's laws of motion. Okay, we also have the Hamilton's variational principle is used to derive the so-called the Lagrange equation of motion. Okay, Hamilton's variational principle. Again, sa math, note getting variational principle sa math is used, take note, to derive the so-called Lagrange equation of motion. Okay, of motion. So basically sa Lagrangian mechanics is ang pinaka-heart niya actually is kaning the Lagrange equation of motion. It is a differential equation. Okay, it is a differential equation that is equivalent to our in Newtonian mechanics. This is equivalent to the second law of the Newton second law of motion. The F equals ma. The Lagrange equation of motion uh, can be expressed or the F equals ma can be derived from the Lagrange equation of motion. So doon na sila connection ng Lagrange equation of motion o ang second law of motion, the F equals ma. So later we will derive that one. Na ako yung Lagrange equation, gikan sa Lagrange equation of motion, ma-derive na ko ang F equals ma. Okay? So we will derive that one later using the so-called Hamilton's variational principle. Okay? It also shows how Lagrange we also have this statement show how Lagrange equation of motion. By the way, the Lagrange equation of motion is uh, for a conservative. So take note na ako a conservative system. Okay? So naay lahi nga form ako ang Lagrange equation for conservative system and for non-conservative system. Take note, non-conservative system means muad na ko mga non-conservative forces like friction, drag, air resistance, and so on. Okay? If there is no air resistance, there is no friction, then the system is conservative. So there is a corresponding equation, Lagrange equation for that motion or for that system. So show how Lagrange equation of motion need to be modified when generalized forces of constraints are a consideration. So doon na po tayo gitawag nga later gihapon, doon na po tayo gitawag nga Lagrange multiplier if there is equation of constraints sa imong system. Okay? Say for example na ako'y object, okay, na ako'y object, ibutangan nimo siya sa kani nga shape, semicircle nga shape. Then question is what will be the equation of motion of this object nga nasa taas? Mo slide ba ni sa padulong ubos, no? Or mo ligid sa padulong sa ubos or diri ba siya or diri ba ka? So there is equation of constraint nga kaning imong semicircle diri. So question is what will be the behavior of this motion of your particle. Okay? So naay problem later nga if I have this pila ang minimum nga angle. We will answer this one later. Pila ang minimum nga angle sa imong object alisir siya mo slide pa ubos. Okay? So naana siya question nga ana. So nakoy semicircle, so nakoy semicircle for example, butangan nimo particle sa taas and then ang buhaton is naay minimum nga angle nga dili pa siya mo slip away. Okay? Nga dili pa siya mahawa sa imong semicircle. Question is unsa na siya nga angle. Okay? So later I will answer that one later. So doon na tayo gitawag nga equation of constraints. Okay? So pwede na to i-modify ang Lagrange equation of motion when there is or when you consider equation of constraints. Okay? So Lagrange equation of motion needs to be modified when generalized coordinates. Okay? Sige lang, no? Ato lang i-discuss later. Forces of constraints are a consideration. Okay? So the point lang man ani sa Lagrangian is once I have a system, then you will need to extract the Lagrangian equation of this and then put it in the Lagrangian equation of motion and then do the math, do the differential equation, you will get the motion of your particle in the system. Okay? So Lagrange equation of motion can be modified if I have a force of constraints. Okay? Okay? So muna yung pinaka-hard ano no kaning if makadungog kag Lagrange multipliers Nagyapon ni sa math, okay? Nagyapon ni sa math. Magamit gyapon mo sa mathematics. We call this, I think, dani sa differential equation. Nakaabot mo maning Lagrange multiplier sa math sa DE ninyo. Lagrange
Wala,
multiplier.
sir.
Okay. Mo taman sa math eh. Sa DE. Ano lang? DE. Kanang kuan lang katong
Operator, sir. Differential operator.
operator nga nakaabot mo tong mga particular solution ana. Kabot mo to no siguro no. Pinakauna man to. Non katong homogeneous solution kato.
Yes,
Non-homogeneous.
sir.
Kabot mo to. Okay. Mayo. Pero amo na po Lagrange multipliers.
Wala pa, sir.
Okay. Sige. Discuss na sa diri no. The Lagrange multiplier and so on. Okay. So, yeah. And the last one in this topic is we will present the so-called D'Alembert's principle. Okay. D'Alembert's principle. Nagip ni sa math. Okay. And use it to derive Lagrange equation. Okay. So, natay pila ka bullet points na ako'y upat to derive Lagrange equation. Okay. So, first, in this chapter, nato ipat lang ka main key points. We have variational principle. Okay. And convert, you will verify that the using variational principle, Hamilton's variational principle, ma-derive nimo tong laws of motion, Newton's laws of motion, the F equals ma. And also, ma-derive po na to, second key points is we have, using that, we derive the Lagrange equation of motion. Then third key points is we have a modified Lagrange equation if there is force of constraints. And the last one is we have the so-called D'Alembert's principle. And from this, ma-derive po na to ang Lagrange equation. So, at actually natay duha ni natay pinsalas nga topic is we have this Hamilton's equation and Lagrange equation. Lang tara to kung asay unsay diferensya sa duha later. Okay? So isa-isa na to ni no. First is so ito the Hamilton's variational principle. Take note, lahi na siya no, lahi na nga ako ang mga topic, no? Lahi na ang concept nga itong ginagamit sa Lagrangian mechanics compared to Newtonian mechanics. Newtonian mechanics is all big. It's just equal to F equals ma, and that's it, no? Ang nakasayon sa Newtonian mechanics is isa lang, simple lang yung equation, F equals ma, then you can answer all of the problems. And not sometimes lisod siya, but yeah, not all problems kay magsayon ra sa sulmon using Newtonian mechanics. That's why natay another method, another mechanics, okay, another field. We call this one as Lagrangian mechanics to answer that problem. Okay? So, dunay lisod nga problem nga dili ma-solve sa Newtonian mechanics nga ma-solve nako sayon sa Lagrangian mechanics. Okay? Pero kung sayon lang imong system, just choose F equals ma, then you will get the answer. Okay? You can describe now the system. But kung maglisod-lisod na, lisod na imong problem, imong system, then nga maglisod ka gamit anang F equals ma, then use Lagrangian mechanics. Okay? Ang naka-diferensya pod sa Newtonian ug Lagrangian. Newtonian is kung nakay problem, mag-draw pa kag mga free body diagrams, tama. Naba kay mga arrow-arrow, no? Arrow sa normal force, arrow sa friction force. Daghan kung what if na kay pulo ka force nag-act ato nga body, then ipag-draw pa nimo tong mga arrow and so on. Right? And then once masayop ka pagbutang sa arrow, then using F equals ma, F equals 0, then sayop imong arrow, sayop imong mga forces, then automatic imong equation nga mga nakuha is automatic wrong na to siya, no? Sakto? So, it's always based on the free body diagram. So if wrong imong free body diagram, then wrong imong equations using F equals ma and F equals 0, then wrong na din tanan imong calculation. Whereas Lagrangian mechanics, no need to put the no need to draw free body diagrams. Okay, there's no need for you to draw free body diagrams. There's no need for you to um, draw all the forces acting on the body, but you only need the two things, the kinetic energy and the potential energy. Duha lang kabo. It's all about energy, not the forces acting on the body, but it's all about the energy in your system. Okay? So once kabalo ka, asa ka padulong ang motion, kana laman. Padulong ang motion, then you will get the velocity, the x dot, the kinetic energy, the potential energy, kanos a negative imong displacement or what. Kana lang itong hunahon sa Lagrangian mechanics. So kung ang Newtonian mechanics is all about forces, drawing of forces acting on the body, Lagrangian mechanics is all about energy, mechanical energy on your system. Okay? Masayon siya. Anong masayon siya? Because energy is scalar quantity, right? Kinetic energy is di na siya kinahanglan mukha pag direction. Okay? Uh, and then potential energy di po ka kinahanglan sa direction because energy is a scalar quantity compared to force which is a vector quantity. Okay? So mo na kalayan sa duha. Okay? So yeah. So later I will derive that the so-called Lagrange equation of motion. We will derive that one later and then we will use that to solve many problems, many complicated problems na sa many complicated classical problems like kabalo man mo solve og ano kaning atud machine no, sakto ba? Kabalo man mo solve og atud machine, sakto? Using Newtonian mechanics, we know how to solve the acceleration of this atud machine. What if butangan ako sa another one dire, we call this one as double atud machine. Kabalo puta mo solve, okay? Kabalo puta mo solve og double atud machine using Newton's laws. But the difference is formula in my opinion masayon solvon ning double atud machine in using Lagrange mechanics compared to Newtonian mechanics. But again, makaya gyapon nato na pag-solve sa Newtonian mechanics. But kana lang no, kamo mamili kung asa mo unsay mechanics inyong gamiton. Okay? So last time 2016 to 2016. So we presented the sa tunga study na mo kang prox nga study no, we presented the very simple problem kani nako inclined plane. So nag-present mi ani sa katong dakon nga workshop sa Davao sa mini prox. So si prox mi nag experiment, okay? And then nasa inclined plane and then I have an object here which has a radius r, okay? And then this one is rolling without sleeping. So gatuyok siya while gapadulong siya diri sa ubos, okay? So in this case, in our paper, we solve this one using Lagrange equation, not the Newtonian mechanics. Solve bang hapon ako na using Newtonian mechanics, no? Makuha na ko ang V dari if I use Newtonian mechanics na ako'y rotational motion nga part, na ako'y kinetic energy nga translational and rotational kinetic energy, I can solve for the velocity at the bottom of the inclined plane. But among gibuhat ato is we solve this one using Lagrange equation of motion. Okay? Using Lagrange equation of motion and then we do experiments. Nag-experiment si Prox ato like gikuha niya ang time from here to padulong sa ubos. Okay? So instead nga nagamit mi og kanang stopwatch nga kanang on off lang, naman na error, right? Na error no? Kay di makabalo ka na sa kamo stop or madili kag tuplok or what. So naay gamay nga diferensya. So ang among gibuhat is we have na ako stopwatch kaya pa na mo gamit pero gikuha na mo tong wire. Okay, gikuha na mo tong duha ka wire dara. Ang isa kay gibutang na mo sa dire, ang isa kay gibutang na mo sa dari. Okay? In such a way nga pag maigo siya sa bola, muon siya, mo start ang time, and then pag abot diri sa end, pag maigo ning bola sa kaning wire dari, mo stop din ang time. So in that way, we reduce the error Okay, we reduce the error using this kaning modified na stopwatch. Okay? Using this modified nga stopwatch. So instead of kanang tuplok-tuplokon lang nako naman na sa error kay na-delay sa imong pagtuplok. So ang gibuhat namo kay giguba na mong stopwatch. I-extend na mo wire gamay. Extend na mo wire na ko start and end. Then I will get the time. Then get the error statistics of it. The theory. We did the theory using Lagrange equation of motion, and we also did the experimental using this one. Okay? So, I think makaya ninyo buhat po, no? Kanang stopwatch nga instead of kanang magtuplok lang ka, kani lang, masyada siya, no? Start and end. Duha dito, giparallel na mo, no? Duha ka buk diri, tapos duha ka buk diri. Kay kabalo mo ko nga pag matuplok na diri, start. Pag matuplok na po diri, kay stop na po dayon. Okay? So, ingana ang iyang form. So, pwede din ako ni yeah. Pwede ni modify ang stopwatch. Pwede na. Lugay na ni siya, no? Pwede na ako ni nindot ni siya. Hindi sa balikan. Anyways, so again, we use not Newton mechanics but we use Lagrangian mechanics to do this one. Okay? And we presented it to Dakon International Conference sa Davao. Ambot nga dawa to siya. Okay. Ambot nga dawa to siya. Sige. So let's continue. We have Hamilton's ibalik na ako, no? Hamilton's variational principle. Variational principle. This is an example of a Hamilton's variational principle. An example. Okay. So, ang Hamilton's variational principle mo na yung equation. Okay, Hamilton's variational principle states that Hamilton's variational principle states that the integral, this integral j, okay, this integral L dt. Sometimes we call this one as principle of least action, the LDT. If you read Feynman path integral, doon natin makita ang ingani nga term sa Feynman path integral. we actually call this one as S sa Feynman path integral, the integral of LDT. Okay, sometimes we call this one as principle of S is principle of least action. Okay, so somewhat muna ang principle, we call this one as Hamilton's variational principle. The J here is just equal to the integral of L dt. Take note is time, dt is time, runs from t1 to t2, and then this L is a very important term sa Lagrangian mechanics. This L is called the Lagrangian. Okay, L, take note, is called the Lagrangian. Okay, we call this one as the Lagrangian. So mupod tong, if you read Feynman path integral. Take note, Feynman path integral is a quantum mechanics na field. Nasa sa quantum mechanics na field, but ang gibuhat ni Feynman kay gigamit siya og principle from classical mechanics, which is we call this one as Lagrangian. Ang Lagrangian kay classical mechanics na siya nga concept. So si Feynman gigamit niya ning classical concept nga Lagrangian to solve quantum mechanical problem. Okay, so nindot kayo no gi-connect niya ang classical mechanics ug ang gi-connect niya ang classical mechanics ug ang quantum mechanics nga field. Final path integral is quantum mechanics, but there is this inside the final path integral there is this Lagrangian which is classical which is in classical mechanics na field. Okay, so L is the Lagrangian. So this J, which is equal to the integral of L dt, is taken along the path. Okay, along the path of the possible motion of a physical system. So mura na siya actually og kuhaon nimo ang pinaka least nga path, okay? Sa tawag ni for example na ako'y fixed point 2 points, okay? So na ako'y say gikan ko diri ug padulong ko dira nga point, okay? I have point A and point B. So na ako diri gikan. Question is unsa ang pinaka mubo nga path para makaadto ka sa B? Ang pinakamubo is a straight line. Sakto? Ang pinakamubo nga path is a straight line. Daghan man siya klase-klase nga path, right? Again, if you go from this point to this point, daghan siya klase-klase nga path. Say, paana pa dito, pabawbaw pa ka, ingani diri, naabot pa ka diri, hangtod sa naabot ka na nga point and so on. So, daghan kasi possible nga path, right? But the sure path or the shortest path nga gikan sa A padulong sa B is this line here. Okay? Yes. Jay Galos. Jay? Hello? Hello, Jay?
Naklik na sir, naklik.
Okay. So, if you go from point A to point B, there are many possible paths, okay? Na layo, na duol, but ang tanaw nimo, unsa ang pinaka shortest nga path is this line here. Okay? In classical mechanics nga point of view, ang pinaka shortest sa math pod, no? Ang pinaka shortest nga path is a line. But pag abot ni kaning gitawag nga mga geodesic na, no? Kaning mga curve na, no? Na nakay curving of lines, for example, nakoy band paper, no? For example, nakoy band paper. Ngani. Nakoy band paper, no? Ngani. This is your plane without curvature. If mo tawa ni kani makita ko ninyo kani nakoy papel, no? I have 2 points. For example, nakoy point 3, point A o point B. Kabalo ko nga ang pinaka shortest nga path if kanila nga plane, ang pinaka shortest nga path is a line from this point to point here. Okay. Pero napoy another concept ani. Ang pinaka shortest nga path daw is if you curve this one. If curve nimo, kulang tanong mo i-curve nimo, ang pinaka shortest nga path is not that line, but ang pinaka shortest nga path is kaninga line. Kaninga point. Kaninga line. Ba? Kung kana lang, pinaka mubo nga path is this one, right? But when you curve the plane, kung ibawag nimo na nga plane, ang pinaka duol na karon is kaning kaning distance between this plane and this plane here, right? So diyan na rin moabot tong diyan na rin mo kwantong mga wormholes like that, yung mga space curvature, space-time curvature, and so on. So kana, no? But in classical, if you do the math by Hamilton's variation excuse, by Hamilton's variational principle, the shortest path will be this line here. Okay, the shortest path will be this line here. Excuse. Okay. So take another physical system is an extremum. So what do you mean by extremum? Kung may kog extremum, it means that you need to derive, tama ba? Sa math pod, if you want to solve for the extremum, the maxima, minima, what will you do is you have a function, you need to derive that function, set it to 0, then you will get the maxima and minima of that function. Sakto? So it's all about, when you say maxima, minima, it's all about derivatives, the derivatives of that function. And when you say derivatives, it's all about variation. Okay? So change, no? Gamay nga change, okay? Kung may kong derivatives, gamay nga change sa imong function, we call that one as variational. That's why we call that one as variational principle. Gamay nga variation, okay? So take note, extremum means you need to derive it, okay? You need to get the variation of that function. Say j, get the smallest variation of that j and so on. So extremum when evaluated along the path, okay? Along the path of motion of motion that is the one actually taken. Okay, that is the one actually taking. So now that is the one actually taken. I have a function equal to this, right? Um, okay. Okay. I have the function equal to this, where L is, take note, the Lagrangian. And what do you mean by Lagrangian? Lagrangian is just L is just equal to the difference of the kinetic and the potential energy. So take note of this. So Lagrangian is equal to T minus B, where T is the kinetic energy. So muna ko gingon, no? Ang Lagrangian mechanics, it's not all about the forces, but we can derive the force. But it's all about the mechanical energy. Okay? So our T is the kinetic energy, and our V is our potential energy. Okay? Take note, it's the difference between the kinetic and the potential. Namang po'y later, namang good po'y gitawag na T plus V. Okay? But we call this one as Hamiltonian. Okay? Hamiltonian. But, dili siya ingani siya form, but somewhat, ang iyahang definition lang is, di siya definition, but you can equate it to the kinetic energy plus the potential energy. But you must write it in momentum nga, in terms of momentum P. Okay? Hamiltonian. Okay? Hamiltonian. So, madiscuss gapon nato ni siya at the last part sa ato ang chapter 7. Sa kaninga chapter. So, once I know the kinetic energy and the potential energy, I can solve now for the Lagrangian. Okay? Say, say harmonic oscillator. Okay? So, when you say, for example, harmonic oscillator. Ang pinakasayon nga Lagrangian is ang free particle there, no? Free particle. Okay. Free particle. Meaning sa free particle is, kung free particle, there's no potential energy. Okay, so the Lagrangian is just equal to 1/2 times mx dot square. Okay, so this is the Lagrangian of a free particle. Okay, 1/2 mx dot square. Okay, it's just the kinetic energy. There's no potential energy. That's why gitawag siya nga free particle, because free lang siya ga move around the space in the system. So there is no potential energy. There's no potential energy nga ga-bound ato nga particle. Only the kinetic energy na. Yes, Julius?
Ay, katong pag ano, sir ba, pag-defend nilang ROA, sir.
Yes, yes.
Na sila i-mention na, ano to siya, Langevin?
Langevin equation.
Langevin.
Yes.
Unsa na sir?
So somewhat related ra siya sa Lagrangian, but salay siya nga field. Kani mga Langevin kay sa statistical mechanics na siya nga field. Kani mga Langevin equation. Kani Brownian harmonic oscillator more on dito siya dapit sa statistical mechanics na field. Ako'y with fluid, basta Brownian kay butang nimo sa fluid, no, immersion siya sa fluid and so on. So more on Langevin is more on in the statistical mechanics field na kuan. But somewhat nasa relationship between not the Lagrangian but the Lagrange equation of motion. The equation of motion itself, the differential equation. So somewhat related ra ang Langevin equation sa differential equation of harmonic oscillator, of damped harmonic oscillator, and so on. Okay? Okay ra?
Okay.
Langevin. Yeah. Sa ato sa classical mechanics, gitawag ra na siya nga equation of motion. Okay, because once we know the Lagrangian, we can solve for the equation of motion. Okay? Ang dito sa ilaha, doon ako'y Lagrangian gihapon, makakuha ka Lagrangian gihapon nato. Pero I think there's no need for you to get the Lagrangian. Automatic or diretso na ka dito sa ang Langevin nga equation. Okay, mo matay mong solvon nga. Mo matay mong solvon. That is a differential equation, then you need to solve that one. You need to solve the solution of that. So, nga na lang, no? Okay? So, again, for free particle, there's no potential energy. So, only kinetic energy ang naa sa imong system. So, therefore, the Lagrangian is just equal to 1/2 mx dot square. X dot is the velocity, right? X dot x dot is our velocity. For harmonic oscillator, doon ako'y duha, no? Since ang harmonic oscillator is na siya gitawag nga elastic potential energy, sakto? So you may write this as na ako'y, of course, na ako'y kinetic energy because your oscillator is moving also minus 1/2 kx squared. Okay? Ako minus 1/2 kx squared. Somewhat decay kaning k kay pwede po na ako siya isulat as kasagara kay dili k ang gamit, no? Kasagara dili k ang gamit, pwede na ako nisulat as 1/2 m omega square x square. Okay? The k here is m omega square. The omega is the angular frequency. Okay, i-omega lang na akong gamay. Kani kay omega man ang adako, no? So omega square. Okay? So this is the harmonic oscillator of the Lagrangian of the harmonic oscillator. And notice, based from this, take note, later, no? Later, ma-derive na ko ni later. Based from the Lagrangian, masolve na ko actually ang equation of motion for harmonic oscillator. Okay? If I have this Lagrangian, and you know that for harmonic oscillator, makuha na the equation of motion for harmonic oscillator is given by this, right? Mx double dot, so ito, equal to kx. Sakto ba? Equal to kx. So if you do, this is a differential equation, we have mx double dot minus kx equal to 0, or you can do it as x double dot minus k over m x equal to 0, or you can do this as x double dot minus omega square x square equal to 0. Sa'yo play plus din, no? Plus din siya. Because this one is minus. This one is minus. Okay? Kani, you derive this one based from the concept of F equals ma. Sakto? It is based from the concept of F equals ma. But if I use Lagrange equation, if I use Lagrangian mechanics, first is you need to establish what is your Lagrangian of the system. Okay? You need to establish, or you need to get first the Lagrangian, and from that Lagrangian, using the Lagrange equation of motion, you will get actually this one. You will actually get this equation of motion of the harmonic oscillator. Okay? So ingana siya, no? Ingana siya. So nasa somewhat connection sa sa ako ang F equals ma, which we will discuss this one later. So wa pa na ko i-derive ang, take note, lahi ang Lagrangian. Lagrangian is just an expression, okay? Lagrangian is just the difference between kinetic and potential energy. Lahi ang Lagrangian sa Lagrange equation of motion, okay? Take note, lahi ning Lagrangian kani gamay to lang nato ni siya to solve the equation of motion. So lahi ning Lagrangian sa Lagrange equation of motion. So to be confident siya, to be Lagrange equation of motion, to be derived pa ning Lagrange equation of motion nato later. Okay? But first, we will you have to know how to get Lagrangian of the system. Say for example, kung free fall lang ka, then the Lagrangian is just equal to 1/2 mx dot square. Kung free fall lang, no? Free particle, subjected lang siya sa gravity. Dili dahil, no? Dili siya free particle, no? Kaya subject man siya sa gravity. So therefore, there is potential energy. When you have this object with mass m, and then this is falling down sa ground, okay, which has a height y, for example, then what will be the Lagrangian of this? Kung sa akong Lagrangian ani, take note, Lagrangian is just equal to t minus v. And in this case, your motion is along y, so therefore your velocity is equal to y dot, tama? So, you can write this as 1/2 my dot square. Y na akong gamit, no? Because your motion is along y, so para lang, anyways, y and x are just distance or displacement. So, say your motion is in vertical, so I will use y as variable for the distance or displacement. So this is the kinetic energy. I-minus na ko siya sa potential energy here, the potential energy of this mass, which is located y above the ground is equal to mg times y. So basically, for free fall, okay, for free fall, not free particle, for free falling bodies, the Lagrangian is basically equal to the 1/2 my dot minus mgy. How about sa pa nga mga sistema tong panggali? Harmonic oscillator, okay na, no? Free fall, okay na pod. Yung sa palain. Wala na ba? Like this one, no? If I have atud machine gapon, double atud machine. Okay, so na ko M3, M2, M1. So sa kani, you need to set variables along kaning imong M1, kaning M2 gyud mo M3. So doon ako yung mga y dira, y1, na ko y2 dira, and so on. Then do the math comparing all of the length of this one, then get the Lagrangian by just taking the kinetic energy of M1, kinetic energy of M2, plus kinetic energy of M3, minus the potential energy of these three, you will get the Lagrangian. Okay? Yeah. So, ingana lang, no? Set first the Lagrangian, which is just equal to kinetic energy minus the potential energy. And once you know the Lagrangian, masolve nimo everything or masolve nimo tanan ang equation of motion. Okay? So, yeah, that's it. That's it for today. Kung mali imong Lagrangian, okay? Kung mali atong Lagrangian pagkasulat, sayop atong Lagrangian, then automatic sayop na pud ang ato ang makuha nga equation of motion. Okay? Makuha nga equation of motion. Okay? I think dira tama, no? We will derive later katong F equals ma later using variational principle. And then we will also derive tas pa rin, no? Ang variational principle. Dugay-dugay pa ta mag generalized coordinates. Ano to? Yeah, dugay-dugay pa ta mag-solve og mga problem like kani. I think nahatag na ako na sa inyo, ano? Kaning nako inclined plane, nako mass which is moving to that direction, and ang sulod sa mass is na pendulum. Okay? Duha ka mass, no? Kaning block o kaning pendulum nga nasa sulod. So nakoy box, butangan nimo pendulum sa sulod, and then this one is moving to that direction, and then the pendulum is also swinging. Question is, what will be the equation of motion for box and for the pendulum? Okay? I also have this kana then ako pendulum sa ubos. This one is moving. Kana this one is also move swing pa sa patulong dira. So what will be the equation of motion using Lagrangian mechanics? Okay, I think maglisod tag solve using Newtonian mechanics sa kaninga problem. I also have double pendulum. Nako ingani. Tapos sumpayan na po nimo isa ka pendulum. Then use kani mag-swing ni sa, kani mag-swing po na. Another one is na ako'y spring ni spring ni siya. Spring po ni. So how many degrees of freedom? Mag-swing na siya at the same time mo stretch o mo compress po ni imong buong spring. So magana na siya, no? Magsayaw imong object. So we will solve this one later. We'll solve this one later. So medyo taas siya actually. Taas siya gamay. Yeah, taas. Okay? So yeah, that's it. Do you have any question?